Hi everybody, my name's Peter Marshall. I'm a technology evangelist working in the Apache Druid community team at Imply. In this video we're going to look at how we can use Druid to treat data when it's ingested into the cluster. Ingestion's first job is to create shards of data that can be distributed and replicated around the historical nodes in the cluster by the coordinator process. When we ingest data, Druid creates a timeline that's made up of sequential intervals. You may see them called time chunks. And each of those intervals is made up of those distributed packs of data that the coordinator is looking for. Technically, they're called segments. In streaming ingestion, Druid creates different segments by watching specific partitions in the stream's topics, meaning that we have some segments that relate to one set of partitions and some segments that belong to other partitions. Sometimes it's helpful to apply a different sub-partitioning scheme. Perhaps there is some filter that we always apply when we query this data set, in which case creating segments that relate to specific values in the dimensions will speed up the querying. And we can do that by applying hashes and ranges through Druid's batch ingestion features. I tell Druid what the format of my data is, whether that's JSON or awk or Avro, whatever it might be, and what period of time each segment should cover in the ingestion specification. And the Druid console helps you build that JSON document interactively, but you can also define it manually in the console's editor or submit them over an API, say from Airflow. The ingestion specification also includes a section that allows me to apply row-based filters, and that means I can select what data from the source I want to ingest, and I can also do row-wise transformations in real time as the data comes in, and that allows me to manipulate the field values before they are made available for query through Druid. So now I've ingested some data and I have my timeline that's made up of segments. What does my ingestion task do next? Well, as data comes in, it's going to do a bit of a magic trick. It's going to turn my row-wise data into a format that's specifically designed for those ad hoc, explorative analytics use cases that we see so many people have implemented across the world. Druid's going to columnarize the data to power column-wise statistical analytics. And it's going to dictionary encode and bitmap index each of those columns to speed up filtering and sorting and group bys, and it's going to use type-aware compression for optimal use of storage. Let's work through an example and see how that happens. So here's an example data set for an online shop. I have a row per transaction that tells me when the transaction occurred, who was involved, what they did, what that did to the stock levels, and how happy they were, or not happy, after the transaction was complete. Remember, this data was written at high speed. When it arrived inside Druid, as it does in many databases, it's row-wise. The computer wrote this out like it was using a pen from left to right. If I want to know average satisfaction, I'm going to have to read row by row, add up the satisfaction number and then divide by the number of rows. And as you might expect, that kind of process, well, it doesn't scale cost effectively to millions of rows a day, let alone millions of rows a second, because I'm reading a whole load of data into memory that's inconsequential to the question that I was asking. So Druid has two tricks up its sleeve. First, it columnarizes the data. Now, when I ask, what's the average satisfaction figure, it's able to read data only from the satisfaction column and ignores all the others. And this mechanism enables you to analyze many more columns than other systems do, high dimensionality data, because columns are stored and analyzed separately. Secondly, remember our timeline, it's made up of periods of time. So notice here with the arrow, it's pointing at the time column. This column of satisfaction values I'm looking at is constrained to a particular time period. In our example, just 12:30 until 1 p.m. And this has two benefits. One, when I'm asking about a particular period of time, Druid can intelligently determine which segments it should go and look at. That's time-based pruning, as it's called, and therefore it hunts through much less data. Secondly, when I want to compare what happened today at this time to yesterday at another time, Druid is able to execute that query in parallel because the satisfaction figures for each period are in different segments and therefore are processed by different CPUs. With lots of fast arriving data, like this talk, in fact, it becomes difficult to keep up. It's like trying to keep up with your boss in a one-to-one meeting where everything they say is important. Well, in the mists of time, instead of writing each word down in a meeting, note takers would use a codex, like this one. A codex allows us to turn this flow of data into a codified version. It is much smaller to store and it's much faster to read. And Druid does this to our dataset automatically. So watch the who and the what string columns in our data. Druid creates a codex of the values. It turns Peter into 1, Paul into 2 and Ahmed into 3. The columns themselves have a dramatic size reduction, with integers being stored instead of actual values. And that's great for storage. But how is this useful for analytics? Well, that comes in the next step. It creates a kind of index of the codex, if you like. Druid creates a bitmap index that records the coverage of each entry in the dictionary. You might know these as inverted indexes. Now Druid will use that information for filtering rows based on individual values. It picks out the rows in other columns to look at, and it can use very fast binary operations when I have an AND or type filter. These columns of data that we've ingested are what we're going to use for filtering, for sorting, for calculations, to compute statistical aggregates, and they're the things that I want to find the top n of, or to group my results by, or that I want to bucket results by. The work that Druid has done for us has already helped reduce the size of the data and make it more suitable for statistical calculations on the fly, but there is another tool up Druid's sleeve that will reduce the size even further while still allowing us to do good statistical analysis of the data. Imagine you're working with a team who are happy with 10-minute summaries of the stock and satisfaction levels. They don't need to know what the satisfaction was second by second. And you may discover they don't even want to filter by the customer. They're interested in trends and overall behaviour more than they are in the buying habits of individuals. So what we need to do is to create new measures that span particular periods of time for the stock change and for the satisfaction. And we want to find some way of counting distinct people, but we don't need to know who it was specifically anymore. For this, I need to use Druid's Rollup feature, and it's fair to say that the majority of people using Druid are using some kind of rollup in their production systems. So let's step through the process of rollup, and to start, keep an eye on the when column. First of all, I'm applying a query granularity in my ingestion specification. You can see here that I've set that to 10 minutes. Now, instead of Druid storing each individual timestamp, now it stores just 3, 1230, 1240 and 1250. And that in itself is helpful for cost and for performance, especially when you have millions of events coming in and you need to analyze those. Step 2, let's go ahead and create those new metrics. We take out the stock change and satisfaction columns from the dimension list, and we create new metrics that are the sum of stock and the max of satisfaction. Now in Druid we get a new row for each who and for each what within each time period. So in our sample here, 1230 is recorded in 2 rows. Our first row is for a who of 1 with a stock change of 5 and a max satisfaction of 5, and then a second row for a who of 2 with a sum stock change of 17 and a max satisfaction of 4. But for the other rows though, the combination of who and what means that there are a lot of rows emitted. If I left our specification like this, that high cardinality column, that who column, would continue to cause Druid to output rows every time it hit a different value. So let's deal with that. Remember, our users don't ever want to filter by who, they just want to do trend analysis. So here's step 3. We're going to use Druid's native support for Apache data sketches. We take who out of our dimensions list in the ingestion specification, and we add a rollup metric called who HLL. And now during each period for each what, Druid records a hyperlog data sketch. And we can use that type of data sketch for highly accurate, very fast calculation of distinct counts for each period. And notice now that our high dimensionality column has gone, the number of rows that we get out during ingestion is dramatically reduced. And that's exactly the technique that's used in use cases like application performance monitoring or telecoms network analysis to ingest vast quantities of data, petabytes of data, while providing high-speed interactive analytics. We're seeing the hyperlog data sketch here. That's for those distinct counts. But there are others you should be aware of too. Theta sketches of a set operations. So maybe I want to work out who visited at 1250 but didn't visit at 1230. And quantiles, they're very useful for telecoms and APM. So if I want to work out the 98th percentile of some value, for example. So Druid Rollup has shrunk my data dramatically. That's one of the reasons why Druid queries are so fast. The volume reduction translates into very low segment scan times. And let's not forget those bitmap indexes and dictionaries on the individual columns of data that speed up the filtering and sorting operations and make those group by and top N operations so much more efficient than they would be on the raw data. So what have we seen? We've seen that Druid is a time-sharded, columnarized, OLAP perfected data store, and that these optimizations are what make it awesome for on-demand, flexible, ad hoc, real-time statistical analysis on fast arriving data at very high volumes. All this functionality means you need to be iterative to get to that perfect ingestion specification. That's why the community is here, that's why I'm here. Come on to the Druid channel on ASF Slack, ask questions in Google user groups, there's a Druid user forum, and email us community@imply.io and we'll be happy to help.